Thank you. Thank you.
Ed,
Well,
please take it away and look forward to this.
well, thank you very much, Victor. And I I got kind of a quiet voice, so I'll try to stay as close to this mic as I can. And this is loose and informal. It's early evening, and please ask questions while I talk, and maybe we'll have some time to discuss the real time as well, since there seems to be an interest in tornadoes and storm chasing and things like that. And yeah, from a storm chasing point of view, it's good. It's not good, I guess. We're 200 tornadoes below the national average. But if you own a home or something, I don't know. But
yeah, if you're a homeowner, this is
yeah,
yeah.
and I was fortunate to not get flooded out in Harvey in last August. So, but I am a true meter. I mean, I know where you're coming from, growing up in eastern Iowa. So, okay, there's a lot of history here, and I'll try to get this started right, but this work goes back about actually to the late 1980s when Dr. Klaus Weichmann, who's now retired he worked at the Environmental Research Lab, formerly the Climate Diagnostic Center in Boulder, Colorado. And I started collaborating when I was a forecaster in Cheyenne, and we started to more closely collaborate back in the early 2000s, and a lot of history, and I don't want to take up a lot of my time going through that, but he was looking to extend his work more into the forecasting realm, application of some more of the, in which I guess you can consider the theoretical aspects, including the Earth atmosphere annual momentum budget, which I'll talk about. And how could we help this to make, especially initially it was week 2 forecast, and then maybe more out to weeks 3, 4, and perhaps even on this monthly subseasonal or seasonal issue, which maybe those are some things we can talk about as we go through. But we developed this weather climate linkage framework known as the Global Synoptic Dynamic Model of Subseasonal Atmospheric Variability. And that's what I'm going to try to build up to as we move on here. So let's get started. The gist is that this is a physically based weather climate linkage framework, and there's multiple uses, including diagnostic, real-time diagnostic and attribution type work, and then having a physical understanding of these synoptic variability to slower timescale processes, weather climate linkage, and one way you can look at that. If you can have a complete understanding, including at least some understanding of the dynamics. I like to get into some of the more, I guess you could say, theoretical aspects, but yet I am also like to help with the forecast too. This is where you can help evaluate the numerical models in real time, and also some of this more recent stuff involving predictive modeling, data-driven methodologies. You can help keep some of this stuff honest, and that's again a lot of the work. Victor and I, we're working on several ideas for proposals. We're going to be looking at some of that stuff. One of the purposes was to produce risk assessments for subseasonal timescales. The Climate Prediction Center had done this for decades with the probabilistic forecast for seasonal forecast issues. And we were one of the first, if not the first, to do this for subseasonal, to develop risk, statements. It's all about statements of probability. The probability distribution is about whatever field variable you want, temperature, precip, tornadoes, whatever. And then you've got to make statements of probability after a few days, because as I'm going to talk about, and I could even jump to this as well, while there are opportunities, individual cases where you can get useful skill for whatever weather-sensitive decisions you want beyond, let's say, 10 days or so, on average, predictability is limited after a couple of weeks. That goes back to the work of Ed Lorenz and his 1963 paper. That's what I think. That's one of the references. I've read them, most of them. And an example is when you're in a persistent pattern, and one can argue we've been in a persistent pattern for about 2 decades now. And if, again, as time permits, I'll talk about that. And that's one of the all you guys that want to see a lot of tornadoes this spring, well, that's one reason you're fighting that right now, is this persistent. We've got a lot of reasons that we're having trouble getting strong jet streams in the mid-latitudes. And so that's why you're not getting these deep troughs in the western U.S. and everything else you want to see with that. So I think I'll just leave it there. Again, a key point is our physically based statements of probability. To more intelligently use other objective tools such as numerical models or big data techniques, inverse stochastic modeling, whatever. So let's just go on here. This is just some additional information about our GSDM. Again, a lot of stuff here, but it's based on the Earth atmosphere angular momentum budget. That's the dynamical underpinning. In the Earth atmosphere angular momentum budget, that's basically the equation of motion that you students, I'm sure, can derive pretty quickly, the equation of motion from F equals ma, Newton's second law applied to the atmosphere. And we look at it. It involves multiple time scales. Initially, it was looking at what we call a linear superposition of multiple time scales, and this encompasses large-scale tropical effective forcing, the role of the eddies, and the engagements of these mountain and frictional torques, in at least one example of surface torque processes, and these wave energy flows. And that's just I'm just saying this at a high level right now, one of the purposes that we developed this framework is you've got to go beyond this mainstream teleconnection thinking or index and things like that. For example, this Nino 3.4 index, while I can understand the scientific motivations for that, it's El Nino Southern Oscillation. It's a global phenomenon that involves the entire tropical oceans, and it's a whole spectrum. It's not just cold, warm, and neutral. Just a quick example there. And things like the Pacific North American teleconnection and the North Atlantic oscillation, I mean, and those are not internal modes. They're not forced. There are reasons why those happen. And those are some of the things that some of the motivation for us to develop our framework, and also to help evaluate, to keep the models honest, and again, that's an old, again, linkages of daily weather to climate change. Climate change is a real problem, and again, that's some of the issues that Victor and I will be looking at going forward. Now, the GWO, the global wind oscillation, we detail, the GSDM. We got 2 papers out that we published, about 10 years ago now, 2007, and that's where we actually talk about the overview of the GSDM itself, and then the global wind oscillation. This was to help add more objectivity to our framework. And it encompasses large-scale tropical convection, but also, again, the role of the extratropics, the eddy transports, the surface torques, mountain and frictional torque variability, and as I can show in these phase plots, it is tied to ENSO, El Nino Southern Oscillation, and we use oscillation, cycle, we'll say those terms to help communicate, but nothing in the atmosphere is truly oscillatory. There's a lot of growth and decay. That's what you really, it's something. You've got a lot of fast noise and then maybe slower noise that may be useful for a forecast. So that's just, again, broadly what we did with the GWO to help better bring in the role of internal circulation processes, including that of the jet stream, if you will. And these plots, they're a little more involved, and I don't want to get too deep into the weeds on this. And this is some of the climatologies we use for both the angular momentum and large-scale tropical convection, including the Madden-Julian oscillation. These background blue curves, you can kind of think of that as just, especially the top one, as just variability explained by slow noise. More technically, it's red noise. There's all, white noise is like on a picture screen. Brownian motion might be another way of thinking of it in an extreme case, just completely random. Whereas you can actually get slower variability when you have slower processes. For example, the North Atlantic oscillation, you can compare that to a red noise process, and it's hard to disentangle the two because that's what it is. And there's generally no predictability. The NAO is essentially unpredictable after a couple of weeks, despite what other sources may say. That's just the way it is. And here, this is the relative atmospheric momentum itself. We're just looking at the circulation, and you can see that there is some signal at about 40 to 50 days. Don't worry about what's on these axes here. Just take my word. That's about 40 to 50 day peak. And then this is the time tendency. When you plot the actual variation against its time tendency, that's where you get the global wind oscillation, as we called it. And in addition to what's explained by large-scale tropical convective forces, there's also independent information just tied to processes that drive the polar jet stream. and as well as the topographic forcing, the mountain and frictional torque. You get exchanges, these mountain friction torque index cycle. That, in some sense, that's the old Namias index cycle back in the day. And then we just threw up here again. You can compare that with the MJO when they do occur, about 50 days. And you can see the GWO captures some of this, and as does the time tendency. So I just threw an example of for those of you who maybe have not kept up in climate variability, what the MJO is. It only explains about 15 to 20% of the variability of rainfall in the tropics, which means you got this other variable that's also important, which is what we capture with the GWO, encompasses that. But essentially, it involves organization of rainfall over the equatorial Indian Ocean, and it slowly shifts east. It's slowest over the eastern hemisphere because that's where the sea surface temperatures are the warmest, and then it decouples between the rainfall portion and the atmospheric circulation when you get into the western hemisphere. And that, again, that's partly because your warmest, it has a lot to do with the Indo-Pacific warm pool, where sea surface temperatures are sometimes close to 90 degrees Fahrenheit. So that's why you see slower movement in the eastern hemisphere and then much faster, maybe even at least 5 times as fast once you get into the western hemisphere. So back in the day, people could think it was a miniature warm or cold event, but faster. And this is some of the points from older literature. And models still struggle with forecasting the MJO, let alone the other forms of predictability and rainfall, variability of rainfall in the tropics. So, and I think my next slide actually shows what one of these things look like. And these truly systematic MJOs, nice, and they have become less frequent and since the 90s, and we think that's a climate change issue. But in this case, you can watch it here. Here it organizes over the Indian Ocean and comes across the maritime continent or Indonesia. And then this was actually during a moderate El Nino, where the Western Pacific was quite warm. So it tries to couple, and then it fails to couple during this winter of 06, 07, which in itself is a very interesting case study. In that winter, El Nino, partly tied to this event, got shut down prematurely. And we were able to capture that in real time. Here, I'll let it go again. Nice blow up. This thing slowly, systematically moves east. And we had an event like that this winter, but it was there was other things going on with it too. But it's very hard to get a nice MJO like that anymore. And that's again that's an issue that needs to be addressed more completely. Needs more work. So I'll just move on then. And so what we did, and this is in our first paper, based on the angular momentum budget, we broke up our framework into 4 stages to kind of simplify things. And there's a lot of stuff there, and let's just again try to just gloss over this. But what you're looking at, the dark shading there, those are supposed to be, those indicate anomalies of outgoing long-wave radiation, and OLR, if you're not familiar with that, is a proxy for rainfall in the tropics, cold cloud tops, thunderstorms. Thunderstorm complexes organize and then start to slowly shift eastward. And these are stream function anomalies, but all I want you to get out of this is, here you have anticyclonic and cyclonic circulation anomalies in the upper troposphere. The signs are reversed in the lower troposphere. It's what some people call first baroclinic mode in the tropics, but again, that's a little more involved. But you get this systematic eastward movement from, this is low angular momentum, positive tendency, high angular momentum, and then everything collapses. Now, if you like severe storms, what you want to see is this happen a lot, these 3-4-1 transitions. And especially in the springtime. And in this situation with the convection over the Indian Ocean, again, we're indicating multiple time scales, but all I want you to get out of this is this can favor these troughs in the western U.S. And we did this for the cold season, but this works any time of the year, understanding the differences in scales and things like that. And then convection comes out, you set off this wave train, and this can be a significantly cold pattern in the central eastern U.S. You get subtropical transition from twin troughs to twin anticyclones. And this is your El Nino-like response here, where you've had a complete reversal of circulation anomalies in the tropics, impacting the extratropics with you now get your extended jet and split flow situations across the U.S. And the funny thing is, this winter into this spring, even though we've had convection way back here at times, we've been seeing a lot of this. This just shows you how it's very much not linear. You know, again, this is part of what you're fighting, but for different reasons than just a southward shifted jet across the Pacific. And then everything collapses. Multiple areas of large-scale convective forcing, zonally oriented wave energy flows, and then at some point when these jets collapse, you dig the trough back in the western U.S. And Victor has shown that in a couple of papers now that he's published, and especially the first one. So we've had since our time, this notion of atmospheric rivers has come out that some of you may have heard of. We just had one hit California last week. If you look at a satellite picture, you'll see these cloud bands that are southwest northeast in the northern hemisphere, northwest southeast in the southern hemisphere. You got a lot of active subtropical jets that are at least trying to get going. So we're more or less, if I had to pick, right in here. And we've had this blow up of large scale convection in the central Pacific over the last week or so that has set off this wave train. We're fighting the ridge along the west coast again. That's why we've had the anticyclonic wave breaking and the split flow trough across the U.S. And I'll go on here, and you know, these phase space diagrams, that kind of before, phase space is something that you may have read about in the literature. When you talk about I don't know if I want to say chaos theory, attractors, things like that. Ed Lorenz and other people, and he was the only one. But these started to become a little more popular in the early 2000s, because it's a good way to condense physical information. You can look at it and get a lot of information out of this. And similar to what Matt Wheeler and Harry Hendon did in their 2004 paper with the Mann-Julian oscillation using their real-time multivariate MJO index, for the sake of communication, we constructed a phase diagram with relative atmospheric angular momentum against its time tendency. We wanted to keep the time tendency variation of angular momentum consistent with what they did in their phase plot, although I don't think that was not their motivation was different than keeping the angular momentum budget consistent, but that's what we wanted to do. And so we've called this like GW01, GW02, and this can only rotate counterclockwise in this phase space because they're not independent, they're not orthogonal from each other, as opposed if you were to do, if I might say, EOF phase, empirical orthogonal functions, which are independent orthogonal. So this is going from low angular momentum to high angular momentum. In general, we can look at this. We've had a tendency to want to be shifted toward low AM for actually multiple decades, but especially since the late 90s. And we've seen this year. And wave energy flows tend to be zonally oriented as opposed to following great circle routes, especially if the circulation dynamics are dominating over rainfall in the tropics, which seems to be happening more often than not anymore. And this situation favors what we're seeing a lot right now: easterly wind flow in the subtropics, a lot of ridges in the mid-latitudes. And if you do get a cyclic behavior in a manner of speaking, then you're going to work to add westerly wind flow. The trade winds, gain angular momentum from the Earth because you got the Earth rotating from west to east, and the trade winds blow the opposite, so they're going to pick up. That's all detailed in old textbooks. Palming and Newton's a good example. So a quick one out there. You gain angular momentum, you start to bring the jet southward, and you get circumglobal troughs, and then you dissipate all that. Again, Victor found in his first paper, and we've observed this for years, generally these 7-8-1-2 transitions, if they're at least slow enough and the convection in the tropics can cooperate, this is when you can get this is what you want to see if you want to do storm chasing in the plains, in a manner of speaking. So what we've been doing this winter, and I'll show this, but we've been shifted toward the low side, except for one circuit upward. These lines here, this was just a simple regression that, and I forget I have to go back and remind myself of the details, but the point is that no matter where you start, 2 weeks later, you're either going to converge on the low or high AM side, with a varying magnitude. And you can kind of think of these as attractors in GWO phase space, either toward low or high angular momentum, or if you want, maybe a La Nina or El Nino attractor. Again, even though, again, I want to stress, to me, the ENSO issue is really a whole spectrum. It's not just 3 phases, but yet, you got to communicate, and then all these physical processes that are involved with that. So I hope that at least can make some sense to you folks here. And you can do the same thing for the RMM. This is what Matt Wheeler and Harry Hendon did back in the day. Again, GWO1 against RMM2 to keep the time tendency of angular momentum consistent. You get these wave energy flows that follow these great circle routes. Again, wave 0-1, transition, reversal, and then this is where you don't want to be if large scale convection is involved. If you don't like ridges in the western U.S. And you can see here it's more oscillatory as opposed to where you get this convergence. And that's actually a very important result that we're going to look at that too later down, because this should be published. Okay, so I've already kind of said a lot of some of this stuff, and I've already mentioned several times that it's really a whole spectrum of weather phenomena. I do not like indices. It's because I can go through real-time animations with you, and I will show you behaviors that aren't always in the mainstream. Well, the only point I'll make is with the numerical models is this issue of not completely sampling uncertainty. And I don't care how much you want to multi-model or whatever, you're still, what happens could be completely outside the envelope. That's, again, something to stress. So, and again, this climate change issue is very important. And this is a slide that we put together back in the days, like, over a decade ago. And again, it's, you can look at this as ENSO, MJO, GWO. The GWO actually encompasses the Julian oscillation, actually encompasses rate and large-scale tropical convective variability in general. You can kind of think of this more as interannual variability, then variability tied to rainfall in the tropics, and then internal circulation itself, which encompasses this. And you can kind of think that you have coherent global dynamics, which seems to be difficult anymore, especially in the last several years. And there's a lot of noise. And I'm going to throw this out, there's a lot of noise that's state dependent, that actually depends upon the base state. And we've been seeing that. And that's again, we're going to be exploring that. And there are several papers, you can Google this, that talk about state dependent noise. You've got to identify it in real time, and I'm going to show a case shortly where that was important, including what the synoptic aspects of that is. It's one thing to get into all the stochastic, let's just say mathematics about it, but what does this look like on a weather map, and how can you use it to make a forecast? That's, again, another example of a quick motivation for us developing this weather climate linkage framework. We go through a lot of stuff, looking at animations, SSTs, whatever, and trying to separate signal from noise. And if the data-driven techniques can help, predictive modeling, neural nets, whatever, we'll use that. And then we can evaluate the numerical models. And a lot of forecasters, unfortunately, like to, not even look, just run with the models. And if you're going to have any hope of capturing what might be a useful forecast beyond week 2, that's not a good place to start. I do this every day, and I can spend a lot of time doing this, and I can be pretty rigorous about this. This is the kind of forecast process that, like this sub-seasonal to seasonal effort. I think it was CPC that hosted that, right, Victor? Yeah. I think that's been mainly model driven as opposed to a more complete forecast process, which is, if Klaus and I were still active today, we would have been talking very hard that this is the kind of approach that they really should be taking. Okay, this 13-14 winter, this happened, 5 years ago now, 4 years ago. This was the so-called polar vortex winter, or, an Arctic amplification, for some of you are familiar with that. Of course, that's not what it was, and let's get to it. A lot of text here, and I tend to like, I like details, so you have to, pardon you on that, but A lot of cold, which I'll show in pretty much in the eastern, especially in the middle of the country, while it was warm and dry, drought on the west coast, and Europe was getting hammered with actually a poleward shifted jet in the North Atlantic. And yet there was predictability on this S2S subseasonal to seasonal time scale, and the models pretty much did not get it because of this, which I'm going to show, the Western Pacific Ocean warm pool is what was involved. And it was tied up with a complex interplay involving large-scale rainfall in the tropics, which was not MJO, and in processes in the circulation. And you can look at these RMN phase spaces that Wheeler and Hendon did and not have a projection, yet have very important tropical vector variability going on. For example, multiple regions of tropical forcing where the EOFs just cancel each other out. You've got to understand what you're looking at when you're using these things. We think this was, again, noise dependent on the base data, and that's what I caught in real time. And again, there's my preaching there, is just to, try to understand as much as you can in real time with our approach to help with that. So this is just a global plot of surface air temperatures. This is a seasonal mean. There's going to be variability, but here's the warm Arctic. People are calling that Arctic amplification, and that is a climate change issue. And that's a term that's appeared, I think, in the last 5 years or so. I have to, when that became popular. And there's a warmth in the Eastern Pacific, which left a footprint on the SSTs. Some people call that the blob. It's been called, and it was because there was a ridge there. And let's go on. This was the Climate Prediction Center's forecast, and again, that's it's maybe in some sense a cold event or La Nina type of outcome with wet in the north and dry in the south, and there's what happened. And again, this anomalous dryness, west of the Mississippi River, except maybe some, not just upslope events, but you can see for yourself. And the preset forecast might have even been better than the temperature forecast. Very low Heidecke skill score there, pretty much 0. Anyway, one thing I want to say is that seasonal forecasting is always a challenge in it anyway. So I don't like to be too hard on anybody trying to make a seasonal forecast. It's a very difficult problem, except in some cases, and this turned out to be one of those individual cases. So where I worked before, and Tim Marquis, I think, he knows where I worked, and I was forced to draw these deterministic maps, which I hated with a passion. These should be statements. Mike died, but these should be statements of probability, and again, I had too much cold. This was a let me back up. This was a 6 to 10 day, 11 to 15 day, and they forecast for the first part of January. The point here, this is a 16 to 30 day forecast. Most models were flipping it warm in January, and I disagreed with that. And I mean, once in a while I can actually guess right, I guess. And what happened in reality is that it did moderate for about a week or so in January, and the West warmed up, but the cold came back with a vengeance in the mid to late part of January, just after this forecast period. But I was expecting this flip toward cold. I do want to point out this is a phase diagram. There's multiple phase spaces. It seems like everybody's got their own phase diagram right now, I suppose. And I'm just used to my old stuff. But George Kalatis, who was one of many scientists that I had the privilege of working with at the Environmental Systems Lab while Klaus was still active out there, all you're doing is just looking at the variability of outgoing long-wave radiation. And I think it's 15 north to 15 south. Another thing about me is I gave up trying to remember details about, indices and phase diagram. It's important to not necessarily memorize, but just think about what you're looking at and just try to think in general. Preaching like a college professor I once had, but don't memorize, think. But I think this is plus or minus 15 degrees of the equator. There's a lot of looping around here, and there's been some recent work by Kondrashov and Chekrun and others show that is an imprint of this noise in the system that's state dependent, where something will come out, get back in from this phase space projected. That's the one standard deviation circle, which I probably should explain some of that more. But at this time there was a lot of looping around, and convection was trying to maybe get shifted more toward the Western Pacific. And this is the Wheeler-Hendon plot, but there's no filtering. This is all full field. A lot of looping around, but we finally got the warm pool engaged. And what I'm trying to do here very quickly is relate this time section of outgoing long-wave radiation. That's what I want to get to here. See these three convective flare-ups? Negative being enhanced convection. Here's the scale, in watts per square meter, explain a little bit more clearly here. The first one was back over the Indian Ocean. But the next two engaged the Western Pacific Ocean warm pool. This thing was coming out maybe 1 meter per second, which, I was speculating at the time that could be an insul signal because we had the strong El Nino in 2015-16, at least even though it did not behave like it should have in some ways. But anyway, another aside there. But this was slowly coming out with these blow-ups. And you can see this is not a systematic evolution in phase space like you would get with a quasi-oscillatory MJO. That's the point I want to make. And these two blow-ups, had a big impact on what happened to the weather over us. And just to make a point here about this, engaged the warm pool, started to bring it out. These are SST totals from the Toga Tau website, or Tau Triton. Again, that's all the Pacific Meteorological Environmental Lab, I think, is what hosts this site. But we use a 29C isotherm. This is plus or minus 2.5 north, 2.5 south, 5-day SST average. Warm pool starting to shift eastward as well as the anomalies. And some people could argue, based, if you want to use this Eastern Pacific cold tone criteria, that it was borderline weak La Nina again from that perspective. But we were starting to systematically engage the warm pool. And what I really care about in especially in the colder part of the year is where that warm pool is going to be, and just how how anomalously warm or is it, or it may not be anomalously warm. That's what I really care about. At least from one perspective of having impacts on the weather across North America. And you can all read this text, going through the slide, and that was the response. And this is a seasonal mean, but there was variability within that. But I'm just doing a seasonal mean of 500 millibar height anomalies, and these are in decameters no, meters, I'm sorry. Strong jet across the North Atlantic, hammering Europe, and here's this, some people might call this a West Pacific North American wave train type WPNA, a westward shifted Pacific North American pattern. That's fine. But this is the response we had for that seasonal mean. And let's just keep going here. This is another, maybe more important slide. This is, again, anomalies of outgoing long wave radiation. Dark colors are enhanced rainfall. And these are plots of 150 millibar vector wind anomalies. There's a scale in meters per second. Roughly a 2-week mean in the first half of December. Both these are the same period. Large scale convection was back to the question. You see the divergent outflow, right? Twin anticyclones, downstream twin troughs. But look at this guy out here, way out ahead of the convection. And there was actually, if you go back, we actually had some decent westerly flow in the subtropics back in November. Again, there was stuff going on before this, but I'm just cutting to the chase here. But what happens, convection comes out, hits the warm pool, and even though we reverse the circulation anomalies in the tropics, that's wave 01 pattern, and there, you can ask me why later it's called that. We get subtropical transition. All it did was just amplify a wave train that was already existing downstream, which was forced by other processes, basically due in a nutshell to internal processes in the circulation. And it just amplified it and shifted it a little bit further east, and there's the cold pattern that came back in the last half of January. And that's what I was expecting to happen. This was because I identified what I speculate, that's all I can do, is this noise issue going on, these blowups each coming out further east, engaging the warm pool, circulation response. And even though we reversed the anomalies in the tropics, all it did was just shift the pattern that was already in place downstream and amplified. There's your North Atlantic jet, and there's your WPNA across the Pacific North American sector. And it's situations like this is what caused the warm blob in the Northeast Pacific. That's, again, that was forced by the circulation. And in general, to make a point, you can kind of think where the SSTs force the atmosphere in the tropics or even in the subtropics, depending, if they're especially 27, 28 and higher totals, SST totals. Whereas when you get outside the tropics, it's usually the atmosphere that forces your sea surface temperatures anomalies, outside of 30 north and 30 south. And you know, there's a lot of debate in the literature about the importance of extratropical sea surface temperatures, but broadly what I just said is what dynamically makes sense. And there is this role of the atmospheric bridge, and well, you can search for that online. Michael Alexander and his collaborators have done some good work on this atmospheric bridge issue. But again, that's just an aside. But just again to tell you the importance of tropical SST boundary forcing as part of this noise going on, forcing that cold pattern. And this also has similarities to GSDM stage 2. And although I was actually approached that we may have been capturing some of this noise issue in our weather climate linkage framework, and here is the again that same plot I just showed you earlier during the last half of January. It's very similar to GSDM stage 2. Kind of keep a long story short there, and you can also capture this response with a linear model, and I don't want to. This is work done by Matt Newman at Israel, but I think this is Winkler and others, Monthly Weather Review 2001 to reference. What you got to do is reverse the science here, and you can again get this response. So, once these anomalies are in place, a linear model can capture that as well, even though what was going on in the weather climate system, I think, was anything but linear. So again, it's kind of what some people call mind screw, I guess. So and there's what the numerical models did. This is anomaly correlation at 2-week lead time. So that's just in a nutshell the winter of 2013-14. And I thought I'd just quickly show this winter, and we can maybe segue that to the real time if we have as time permits. Absolutely. And there's some of the points there. Anomalously warm Western Pacific Ocean warm pool. Again, by the people, the mainstream would call this a weak La Nina. Again, I can go off very quickly on anything here, but you don't have to have a strong cold event to get a strong response in the extratropics. Again, whereas an El Nino is your shift away from climatology, whereas La Nina is enhanced climatology. Think of things like that. There's a significant nonlinearity involved with all that. It's 1 + 1 does not equal 2 all the time when we can look at it. But regardless, let's just not get too deep here. And we had this big subseasonal event, strongest in probably at least 10 years. And yeah, there was a sudden stratospheric warming that got involved. It was a split vortex SSW, and there was a circulation shift from January to February, which again we actually caught this, and I think Victor and I may have talked about this a priori too. And again, we've had a very warm Arctic. We've had anomalous warmth in the Arctic now, for at least the last 10 years, and longer than that, depending how you want to look at it. If you look at sea ice issues. Climate change is involved, but exactly the details I think still need a lot of work. I mean this Arctic amplification issue though was not the reason for blocking negative NAO, things like that. There's a lot of care that's got to be you got to be careful when you try to make some of these statements. And again, I'm one of the guys that's going to ask you why. You didn't, you can't be, got to be careful with some superficial stuff. So let's go on. CPC's forecast using the La Nina composite type of, cold north, warm south, and it's likewise for the precip. And that's the right forecast to make. Again, they do the best they can with what they have. And seasonal forecasting is, it's a challenge. And if you composite on Klaus Bolter's multivariate El Nino index for negative cases, I just threw them all there. You can see the response you get. This is temperature anomalies in degrees centigrade for North America. I can have a bad habit of not explaining figures. These are contours of probabilities. That's as they should. These are probabilistic forecasts as they should be. And this is the temperature outcome for essentially less negative MEI cases, which include La Ninas. Here's what happened. This is what was observed. Of course, here's the warm Arctic. So you're not going to get that. That's something else going on. And as far as the forecast, of course, we had the warmth out here. And generally cool in the central and eastern U.S. and we actually had some cold in Texas on average. So but not a bad forecast, and the precip is really not that bad. But of course, we've got this huge drought that's a very significant drought, severe drought now in the southern plains, and they've had some relief in California from at least this atmospheric river event last week helped things out. But if we look at the the U.S. drought monitor, you're going to see a lot of dryness continue to amplify it. I got to wonder, is this going to spread northward this year? And that's things do. We've been fighting it. And Iowa's had drought conditions. Again, this is just observed precipitation. This is not a drought index. And again, you can do a composite on the MEI for the same years, and that dry signal does show up for these negative cases. So that is capturing some of this. So that's enough said, I guess. And this is the seasonal mean average for total SSTs. Here's the cooling along the Eastern Pacific cold tongue, but this is this patch of warm sea surface temperatures, the Indo-Pacific warm pool. Probably shifted a little bit further north than it should be. That's another problem we've been seeing, this northward shift, among other things with global warming, which is part of climate change. And there's the SSTs, anomalously warm. And if you look at, and here the signs are reversed for OLR. Here the warm colors are where the convection was most active, just west on average of the warm pool, which is typical. And this again is the MEI composite, which lines up with what we observed. But and I'm going to get to that. We had a big subseasonal event in January going into February, and this was so strong that this is an activity index that was produced by that Matt Wheeler runs on his website, and maybe we can give some links to these, and so on. But all I want you to see, this is looking at the square root of the amplitudes of the two EOFs, RMM1, RMM, real-time multivariate MGO index. And in general, there hasn't been a lot of it, especially since about the mid-90s, and even since the early 2000s. But here's this spike, mainly from this big event. This is not something that you can predict even at a month lead time. This is something you got to catch in real time. So if you're going to be making these seasonal forecasts in the summer, that's something for the winter, you can't predict that. That can have big impacts on what happens for a seasonal mean. So just again to give you, predictability is so difficult beyond 10 to 14 days, because this is something that is you just got to catch in real time. It's very much stochastic, which is another way of saying random. And these are some of the phase plots for this past winter, which I'll to save some time, I won't go too far into the weeds, but the shift toward the warm pool. This was our subseasonal event. It tried to link up with the warm pool. There was a weaker event earlier, which I'll talk about in a second, but this is George Kaloudis looking at the OLR only. Again, and the variations that you see here are the same as these other ones, which I'll get to in just a second. Shift toward the warm pool. This is the unfiltered GWO, shift toward low AAM, but we had this big event come out that perturbed it, which again I'll show as I move on here. And this is the filtered RMM phase space, and this is unfiltered, which is what I prefer. We had this little event in December, which was actually pretty important, because that may have played a role in setting off this big event that later followed. And you can again see this shift toward the maritime continent, which in a superficial way of thinking, maybe be a combination of what you're seeing here. This is the circulation, this is the convection, and the problem with or at least one problem with these RMM phase spaces is that you are going to capture the circulation from the extratropics. This is plus or minus, I think, 15 degrees of the equator, but still wave energy flows from outside the tropics will impact these. We see that all the time. So that's a phase diagram representation, and we'll just leave it there. Let's just move on. And this is a plot of global relative AAM, the global integral, the global signal, the global mean wind signal, if you will. And this is looking at the zone mean anomalies. And this is our big event. And first it went down, then it came back up, and now it's gone back down again. And even with this huge addition of anomalous westerly flow in equatorial region, these easterlies are just like a barrier. It would not hook up with the mid-latitude jet, which in itself has shifted north of climatology. So that split flow, westerlies, high pressure in the mid-latitudes, and then maybe at times some subtropical jets. So that's split flow. We had a flip toward the end of February into early March, and again, that was driven by those are eddy-driven processes internal to the mid-latitude jet, but that's what helped set off that blocking in the North Atlantic. I look at some time sections of OLR. The fast event in early December tried to hook up with the warm pool, and then we had the slower event that followed it. And you look south of the equator to obviously with the warm pool being shifted south of the equator in the wintertime, in time longitude section of anomalies and totals, it came out further east. And that was all part of what contributed, see if I can go back here, to this big rise right here. The convection was part of it, but there was also other things going on that prevented this from punching through the mid-latitudes, which if you want to see an active storm season, you would want to see these easters get out of the way. You would have wanted to see that punch through. Did not happen. This is the transport. This is actually the biggest term in the budget. This is basically how the mid-latitude eddies are driving the polar jet stream. And you've had a lot of northeast southwest tilted troughs and ridges. That's all I'll say. And then there was this flip, but again we're back to sink in the subtropics, and source shifted way the heck north, even north of where climatology is, where you have that's climatologically where your maximum flux convergence is, and it's shifted north. And again, I did a quick annotation in early February. The convection came out. Notice how everything is shifted north, these anomalous westerlies, and here's the wave trade that actually gave a period of cold and snowy conditions for a little while across the central and eastern U.S. All this high pressure, these are 150 millibar vector wind anomalies. This is what set off the vortex split sudden stratospheric warming. And this was well before any blocking appeared in the North Atlantic. And because there's this idea out there that you get a sudden stratospheric warming, you're going to get a negative Arctic oscillation, and again, it's not that simple. So, and I thought I'd show this. This is from Paul Newman's website. There's the actual observed, which it got above the 9th percentile briefly. That was a major warming, although I've seen bigger than that. But that was not a bad event. And the circulation behavior. This was the December-January mean of 5 millibar height anomalies. Geopotential height anomalies in meters, December and January, along with the surface temperatures in degrees centigrade, and then the retrogression that occurred when the convection came out, set off the wave train, things shifted west, and then there was a significant cold in the middle of the country, and there was about a week there of 20 to 40 below zero morning lows, and again for those who are in the energy sector, here was the big flip in the eastern U.S., and there was some predictability of that. That was predictable. So again, a lot of stuff there. I'll let you, I've already talked about most of this because I want to open this up. And there's a lot of stuff that Victor and I are looking at, this issue of non-Gaussianity. This super rotation is a fascinating area. It's strong equatorial jets, and where the atmosphere rotates faster than the Earth in the global mean. And we're going to be looking at these error spread relationships, and model diagnostics is not something we really talked about, although you're doing that right now, Victor, with the annual momentum budget. And it continues to be, predicting extreme weather events, we've gotten better, but it's still elusive. And again, if you have a much better physically based understanding of the weather climate state in real time, that can better improve numerical models and other types of data-driven methodology, mixed, stochastic inverse, linear inverse models, things like that, mixed statistical dynamical methods, and having better models with a better understanding. That's going to be our only hope of at least getting weeks 1 and 2 right. And after that, we'll see about just beyond what we can do for week 2, other than individual cases. And so I thank you for your time and attention, and welcome questions.
Well rehearsed, 7:59.
Okay.
Yeah, so that was perfect. At this point, we'll open it up for some questions or stimulate some discussion, and there may be some interest to kind of look at what's happening right now and sort of how Ed would go through that framework of diagnosing what's happening now and maybe what we can learn from the current subseasonal pattern. And then, of course, that lays the foundation for what may come here in the early spring. So, but before that, if there's any questions of, and again, a lot of this stuff I know can be technical and
it is
difficult to sort through, but if there's a couple papers out there, at least the 2007 paper, which I think is a good overview and not that difficult and technical to read, that you can get through to kind of get through some of these ideas. So.
And you'll link to that?
Yes, yes, absolutely.
And
of course, the slides will be available if you want to get in the weeds and read the text.
there's my email information. I can send you links to, and I'll be happy to answer questions, and because I just went through a lot of years of research very quickly, and it can, it's early in the evening. It can be easy to take a nap while I'm talking about this stuff, so it's, I was trying my best to, provide some motivation, which is why I referred to the, disappointing storm season for a lot of people right now, where at least you're saving money on gas, so,
Adam, your budget is building.
It really is.
So questions for Ed at this point?
There you go. I mean,
Questions for Ed. Ed's had a long career in the weather service and the private sector, so students, if you have questions about his career, we had a discussion at NIU yesterday about his career at the weather service and the private sector, so let's just open the floor for any questions.
I think you had your hand up.
Gilbert, yeah.
Data-driven question. Different as opposed to going to the source of the data. Will GOES 17 and Himawari 8 significantly improve data acquisition and accuracy over the part of the areas of the globe where we don't have good data?
Okay, the question is, and I probably won't get all restate it correctly, but you're basically asking if the improved high-resolution global satellite image will help better improve data quality acquisition, things like that, in terms, especially the rainfall patterns in the tropics. Okay, first of all, that's a good question for research, and I think people are testing that as we speak right now. Just to first give a question to that, and these are things. Victor and I got a long list of things we want to look at, and that's a very good point right there. Secondly, we've got to get a better understanding of just what the rainfall in the tropics is, because we look at OLR, that can be coarse and things like that, and if we can get a better estimate of rainfall rates, and if you get a better estimate of rainfall rates, and again, I'm not an expert in satellite applications, so maybe you can help me here, but if you know what the rainfall rates are, then you get a better estimate of what? The diabatic heating, and if you get a better diabatic, then you get a better understanding of the mass circulation. It's like, are we ramping up the Hadley cells as this large-scale convection comes out? That can go into better modeling and so forth. And there's a paper, Prashant Sardishmuk and Brian Hoskins wrote a paper about the baroclinic high problem back in the late 80s. And they were trying to use that, and that you can search for that paper online, but they're just basically trying to estimate large-scale tropical diabatic heating using that technique. Satellite imagery, I think, will help with that. Now, how that will help the numerical models, that's a good question, because there's so much other things going on that can trump large-scale heating. So, does that make sense?
Yeah, absolutely.
Thank you.
There's one satellite mission from NASA called NASA
help me out.
Satellite.
Tropical,
microwave system.
yeah.
It's really, it was launched in orbit for that purpose, to try to capture the late heat waves in the tropics.
Yeah, I think that was started in the 90s, wasn't it? Help me out. The Tropical Rainfall Measuring Mission.
Questions? Any questions? Nobody wants to know what the spring's going to be like?
Yeah, we'll go into the real time.
Oh, when's it coming?
Yeah.
Yeah, when's it?
Well, in the Midwest, that's a great
Yeah, I've had temperatures in the 80s in Houston, and now I'm finally getting some rain down there. Hopefully, I won't have my house flooded when I get back there tomorrow, but I won't. We need the rain. So I mean, let me ask you: was this useful to you? At least, because I know this is, I don't know what kind of speakers. This might be on the more technical side.
We've got everybody from Marshall Shepard to Uccellini.
Okay.
And we're in between. So.
Okay.
Yeah.
Okay. So good. And again, I appreciate the opportunity to talk to you folks.
Yep, we have questions.
So what does it mean for the rest of the storm season?
All right, let's go to the real time.
All right, do a little real time.
All right.
It's only 5 after. We can
Yeah, I will.
turn.
Let me see if I can drive
Stuff
this.
should still be up in the tab.
I tried to I hate, again, this is something we're running internally right now. And let's talk about this guy right here. This is the last 90 days. I was talking a little bit about this before before I gave my presentation. We'll slow down a little bit here. We're looking at a plot here. The top plot are anomalies of vertically averaged, of zonally and vertically averaged relative atmospheric angular momentum. They're in angular momentum units, and if you work out the units, it's something. It's like kilograms meters per second squared, and they're huge. 10 to the 24th, but you know, again, that's just getting a little bit, maybe you know, you can work out the units. These are the totals, and the shading are the anomalies. Kind of slow down what you're looking at here. So here's our subseasonal event. A lot of westerly flow. Notice how the contours come south. More westerly flow. And yet, here's the anomalous easterlies, and here the contours are shifting north. Northward shifted jet. And you have westerly flow in the subtropics with ridges in between, and well, high pressure ridges, you know, in terms of surface pressure, at around 40 north, and then low pressure at times in the tropics and subtropics. But this is zonal mean split flow, and look at what's come back now. And that is impacting the variability we're seeing across the country. You're getting these troughs that come in, and what do? You guys tell me what they've been doing. Doing the splits, right? Well, you're seeing that problem is so intense right now. It's showing up in the zonal mean, and it means that we're not just the only ones suffering from that. It's also happening in the southern hemisphere. So this is a global issue right now. This idea of jets getting shifted, you know, poleward in both hemispheres, and easterlies in the subtropics, and these westerlies starting to speed up in the equatorial region. We think that there's a climate change issue with that. And I'll even venture a little further here that if this continues, this could impact the global mean, such as this may go up and stay up like this, even with easterlies and subtropics and shifted poleward. Then you got a case where the atmosphere is rotating faster than the Earth, and that's called superrotation. And there's papers, you know, that have been speculating when could that happen as a result of climate change. You know, I think something like 50 to 100 years I've been seeing, and you know, the funny thing is,
which actually has implications for the length of day.
That's right.
On Earth, so would slow down Earth's rotation.
And speed.
You'd end up with in theory,
a few
25 hours instead of 24. So
yeah,
you want an extra hour in the day? Super rotation is your answer.
Yeah, that would really have to because right now I would say a few milliseconds, but it all depends.
Milliseconds.
Yeah. But still, that's an old reef looking at this angular momentum length of day issue. There's a lot of applications of all this work. So I don't think we're going to get rid of this spring, to answer your question. We're going to be fighting this. And what we want to see, in some sense, not necessarily the reverse, but I'd want to see some warm colors in here. So it'd be nice to get this to punch through and bring that jet southward, and have the tropics be involved with that. And then when the convection comes back around to the Indian Ocean with already anomalous westerly flow in place, and the jets start to collapse, then and we can show this from our composites, that's where you start to get your deep troughs in the western U.S. Good example, that was the winter of 07-08, that happened a lot. And that was the Cedar Rapids Great Flood, my hometown. And there have been some other instances of that too since then. But this is not good for an active storm season, on average, short answer. And this also favors a lot of drought in the mid-latitudes too. Subtropics and mid-latitudes.
Adam, you'll be staying at the Trump Taj Mahal with all the money you're going to be saving.
Prepare for next year.
So,
of course, you're going to have mesoscale variability in there.
Yeah, you're just looking at averages here. And,
that's right.
And this is looking at the last past year again. You know, this is the austral southern hemisphere winter. boreal winter again. Now it's going to be stronger in the winter hemisphere in general. Again, there's the easterlies down there, subtropics, and then we get up to our winter, while it still persists in the southern hemisphere, all shifting poleward. This is just nothing more than a little perturbation and something that's been lasting what may be on the order of decades, a couple of decades now. And we tried to add some westerly flow, and this was tied to some weaker subseasonal activity. And then there was that little blip I talked about, that little rotation in phase space in early December. And then this big guy came along. It tried, but couldn't do it. I mean, it's kind of like the Hulk fighting Superman. I don't know. This is going to be an issue going through this spring, anomalous species in the subtropics. And unless we can get something big to happen in the warm pool and maybe get another event where we can punch through that, that in itself, understand that there's so much noise in the system where things can change on a dime for a couple of weeks. I think a good example of that was what, 2014, May of 2014, where it went from quiet to the El Reno, Oklahoma.
13. Yeah,
13.
Very, very, very quiet. And then you had a flare up of convection, and then you had you had El Reno, but really the previous, that sort of 14-day centered period,
Yeah.
of active troughing and severe across the plains.
So,
and other extreme weather, not just severe.
Right. And Victor and I can show some composites. I would be surprised if there isn't an active window in there somewhere, though. But we'll just have to catch it when it happens. But this, this in general that's not good. That makes sense? More or less.
Yeah.
Catch it in real time.
Now, you were mentioning the stratosphere and getting a little warmer. Now, if I may put on my astronomy expert witness hat.
Please do.
Kidweek National Observatory, okay.
Please do.
But anyway, we've been noticing that over quite a period of time now, maybe a couple of decades, that the stratosphere has been unusually low in opacity. It's been very, very transparent.
Okay.
The two lines of evidence for it are, first of all, very bright total lunar eclipses.
That makes sense.
What's called the Danjon scale on that. And
Okay.
they've been very, very bright. They've been in a 3-4 category.
Okay.
I remember the only zero, I can show my age, was December of ~63. The
You and
moon
me.
vanished. There was no copper color of anything there.
All right.
There was a major eruption of Mount Agung in Bali a few months earlier, and it just made the atmosphere very, very opaque.
Yeah, I
And
know. I remember
atmosphere was
Pinatubo.
very, very black. It just disappeared.
Mm-hmm.
In any case, though, what would happen then? Can you predict if there's a major volcanic
I knew where you were
eruption,
going.
like either Pinatubo or worse yet, like Tambora?
Right.
And what's going to happen to all this?
Well, first of all, you're going to get a big warming in the stratosphere if you get a volcanic eruption, as you know, and it will likely cool the troposphere. That's been shown by several papers, and I mean, I have to go back and look what this year of no summer was. I don't.
1896.
Okay, I think that was that Tambora. Remind me.
Tambora, several eruptions in a row.
Okay, remind me because I forget the date. Okay, but yes, that will have an impact on global mean temperatures, and that's, you see. Let me just go off a little bit. There's this issue, as I briefly mentioned, internal variability versus anthropogenic warming. And another thing that's a volcanic significant volcanic eruption that will have an impact, but it'll only be maybe a few years. So it would be a blip in what could be a continued warming overall of the atmosphere. But I'm just speculating that I don't know. So but yes, a significant volcanic eruption of the scale of Pinatubo or greater will impact surface temperatures. And the question is exactly where, because there's going to be other synoptic variability that you cannot predict, that whatever is going on at the time.
Because I worry about these geoengineering projects where they're going to try and block the sun and simulate a volcanic eruption with injected aerosols.
That's right.
If they do this on top of a Mount Tambora blast, we might have any growing season, for peace sake. I mean, it was
At least at the higher latitudes.
Growing season back when it happened.
Yeah.
Well, that will also happen if our president hits a little red button. Let's try to keep this finger off of that.
Yeah.
All right, any other questions for Ed? Otherwise, we're gonna let him off
That-
the hook. It's a quarter after.
But you know, those are good questions
Yeah.
too. I appreciate that.
Any other questions for? All right, let's thank you. We came all the way from Houston.
Thank you.